Hello, and welcome back to another episode of the Curiosity Monkey podcast. Now, over the last few decades, it's becoming increasingly more apparent that the Earth is warming. Now, this is almost primarily due to increased emissions of greenhouse gases. These greenhouse gases work by essentially absorbing terrestrial radiation emitted by the Earth and then re-emitting it back in all directions. And so some of this radiation is re-emitted towards Earth and some is re-emitted out to space. But this leads to a net warming of the planet. Now, greenhouse gases are essential for life on Earth because without greenhouse gases, the average temperature on Earth would be around minus 15 degrees Celsius. Now, with them, it allows the average temperature to be a lot higher, between 10 and 20 degrees Celsius, and this allows for life on Earth. However, because we're emitting more greenhouse gases into the atmosphere, we are trapping more heat in, and essentially what is happening is we're getting a net increase in radiative forcing. So what I mean by this is more energy from the sun is being absorbed than we are emitting back out to space. And this is causing a net warming. At this stage, climate change is not very unheard of. Most people do accept that is a thing, and most people also accept that in general it is not very good for us as humans and for the planet in general. However, the topic of this episode is that the Arctic is in fact warming at a faster rate than the rest of the world is. Now, there are a few reasons for this, and we'll get onto them, and the mechanisms of how this is happening. But this phenomenon is known as Arctic amplification. So essentially, we are seeing that the Arctic region, so I'm talking about the northernmost part of the world, so the very top, is warming at a rate 2 to 4 times faster than the global average. And we can see this directly through just measuring the temperature. You can also see it from space. If you look at satellite images, you can see changes in the amount of ice that is in the Arctic Circle. Essentially, the amount of ice is decreasing over time. You expect a natural fluctuation of ice during the seasons. So, during the summer season would have significantly less ice than the winter season. But every year, at almost every part of the year, we are seeing that there is less ice. So less ice in the summer than you would usually expect, and less ice in the winter than we would usually expect. And this is providing some problems for a few reasons that I'll talk about in a little bit. And why do I say between 2 and 4 degrees? Why is there not an exact number? Well, firstly, there's a little uncertainty because there's a lack of consensus over the definition of where the Arctic begins and ends. So, if we select an area and define this as the Arctic, and every study that looks on the Arctic amplification takes this area as the area of the Arctic, then it's likely would come to a more constrained number. But also, because the warming in the Arctic is not uniform, some places warm more than others. So if we do not have a fixed definition of the Arctic, and we exclude some areas that are maybe warming more than others, or warming less than others, then our values for Arctic warming are going to be different. In fact, some studies have shown that Arctic warming is 7 times greater than the global average in some areas, which is very significant. Now, this uncertainty is not great because it means it's hard to predict and hard to model what's going to happen in the future, which means our models are more uncertain, and the effects of this melting of ice is also more uncertain. And I guess also a very important thing is, why do we actually care? Well, there are a few reasons. The Arctic, first of all, is not only important for regulating its local climate, but also regulates the climate on a global scale. So essentially, if changes happen to the Arctic, then you will see changes to the rest of the world. So one of these things is because the Arctic area has a lot of sea ice. And sea ice, well, if you've ever been to a place with snow and ice, then if you look down, the surface is very reflectant, yeah. So it's just very bright. Everything comes and is reflected back up into your face. So it is evident that any light that is incident to the ice and snow a lot of this light is reflected back out to space. In fact, 90 to 95% of the solar radiation incident on Earth's ice fields is reflected back into space. So this is very important for the energy balance. And by definition, light is energy in the form of electromagnetic radiation. And this energy, some of it is absorbed by the planet. So in places of land and darker areas, such as the ocean and just darker areas of land, they absorb more of this light radiation. And the absorbance of this radiation causes the planet to warm. So reflecting light and more light back out to space helps cool the planet in the local area and on the planet as a whole. So the melting of ice due to climate change can decrease the reflectance. Specifically, when we melt ice, whatever's below it, such as the ocean and land on some, if you got land ice sheets, the surface below is less reflecting. So you absorb more radiation, and this can warm the planet. The ice melting can also cause several issues, such as, melting of the Greenland ice sheets will cause significant sea level rise. So Greenland is in the Arctic Circle, and it contains a lot of ice which is stored out of the sea, just on top of land, and contains significant quantities of water. So if this ice sheet were to melt completely, then the sea level would rise around 7 meters. And there are actually a lot of cities that are less than 7 meters above the sea level that would get affected. So Amsterdam would almost completely flood, just with a couple of meters of sea level rise. More locally, Cardiff, much of Cardiff would be completely underwater, only a meter sea level rise. So this not only affects some faraway island that may feel insignificant and unimportant to many of us, but also has potential to affect almost everywhere coastal on Earth. This should be very concerning for people living on the coast, especially in areas that are not very elevated above sea level. And it's estimated that both the Antarctic and Greenland ice sheets hold enough water in them to be able to raise the sea level by around 65 meters if they melt. And yeah, that's a significant sea level rise. It would not happen over the foreseeable future, but only a fraction of this rise can significantly affect populations across the globe. And an estimate by the IPCC, which is the Intergovernmental Panel on Climate Change, estimates that 680 million people in the world live in low-lying regions of the coast. So these areas would be liable to flooding, and these people could be displaced. So yeah, that's of concern. Additionally, adding the melting of ice sheets can add in a load of fresh water from melting ice. And this can in fact change the circulation of the global oceans. So deep ocean currents are driven by differences in water's density, which is controlled by the temperature and the salinity of the water. So salinity is just the amount of salts, dissolved salt. Now, the Gulf Stream is one of the main reasons why the northwest of Europe is warmer than it should be. Now, if you take into account that Edinburgh, a Scottish city, is around the same latitude as Moscow, which is a Russian city. Now, Edinburgh is significantly warmer than Moscow, and this is due to the Gulf Stream. So climate change is likely to slow down this thermohaline circulation, which includes the Gulf Stream, and this could drive the UK into a much colder climate and the rest of northwest Europe. We're talking about changes of up to minus 10 degrees change, so that essentially the temperature could go down by minus 10 degrees and make our climate much colder, and it's just not ideal. Additionally, the Arctic stores quite a lot of carbon, so because it's so cold, the ground in the Arctic is cold and often frozen, and this frozen cold ground can store preserved organic matter stored underneath within it. And because it's so cold, the bacteria just cannot work to decompose this organic matter. And during the decomposition process, methane and carbon dioxide can be released. So as temperatures warm, these bacteria can then work to decompose this preserved organic matter and then can decay into methane and carbon dioxide and release it into the atmosphere. So these permafrosts contain the equivalent of 150 years worth of fossil fuel emissions at current rates. So this is a significant amount of fossil fuels that could be released into the atmosphere if melting continues to occur and the permafrost melt and allow for the decomposition of this organic matter. Now, this is a positive feedback cycle, so the more warming you get, the more melting, and the more carbon dioxide and other greenhouse gases are emitted, which then causes more warming, and it's a positive feedback cycle. Also, carbon dioxide is usually the greenhouse gas people are talking about when they talk about greenhouse gases, but methane is also at play here. The decay of organic matter in anaerobic conditions, so conditions without oxygen, can cause the fermentation process that releases methane instead of carbon dioxide. And methane is generally more potent than carbon dioxide, so it can have a greater greenhouse effect and contribute to more warming. However, it should also be noted that methane lasts significantly less time in the atmosphere than carbon dioxide does. So now we should move on to how this Arctic is warming more than the global average. And there are actually quite a few different mechanisms at play here. I think most of them are quite interesting, but we'll start with the first one, which I've already touched on a bit, and it's probably the most obvious one, which is the ice albedo feedback. So as I said before, ice is reflective. And you can see this, if you look at bright snow on the ground, it just reflects a lot of light into your eyes, which is why if you're skiing or something, you usually tend to wear like a ski mask with sunglass protection kind of thing to protect your eyes. So ice and snow reflect solar radiation. So solar radiation from the sun comes to Earth, and most of it is reflected back out to space. And because it's not absorbed, it leads to a cooling effect because less is absorbed. So at higher temperatures caused by climate change, some of this ice melts, which decreases the area that can reflect light back out to space. So decreasing the area of the ice can therefore lead to more absorption in the polar region, which can therefore lead to more warming. So this warms the polar region and then leads to more melting, and then leads to a further decrease in ice area. So this is the first positive feedback I'll talk about today, where the temperature is very closely linked to the amount of ice in the region, and the amount of ice is linked to the temperature. The next one is similar, actually, in its mechanism to the ice albedo feedback, but this one works off clouds. Clouds are quite bright in general. If you go into an aeroplane and fly just above cloud level, and look outside, you'll see that the clouds are very bright, so clouds are very reflective of light, and they can reflect a significant proportion of incoming solar radiation back into space. And this can lead to a cooling effect. So again, they are bright like ice. So clouds are very reflective, they can reflect the incoming shortwave radiation, so when I say that, I mean light, back into space. And they can cool the region. So changes in cloud coverage can cause changes in the amount of reflectance. So if there are more clouds, then you've got more reflectance. If there are less clouds, you've got less reflectance. But remember, the Arctic light cycles are very different to other places in the world. So in the summer, you've basically got constant brightness, and in the winter, you've got constant darkness. So during constant darkness, you do not have the solar radiation to reflect. So if you have more clouds during this period, it doesn't matter if you're adding more clouds because you're not going to be reflecting more radiation because there is no radiation to reflect. However, clouds also absorb the infrared radiation emitted by the Earth's surface and emit some of this back to Earth. So while during the summer months, when you've got the radiation coming from space and having this reflected back out to Earth, you additionally do have this infrared radiation that is being absorbed by clouds and emitted back to Earth. The reflection of solar radiation is far superior and leads to the cooling effect during the summer. However, during the winter, when there isn't a cooling effect because there's no solar radiation to reflect, the clouds do absorb some infrared radiation emitted by Earth's surface and emit this back to Earth, which means during the winter period you have a slight warming effect So you can actually see this for yourself if you take a cloudy night versus a clear night. The clear night usually is significantly cooler because there are no clouds to trap some of this heat back in. But during a cloudy night, it's usually warmer because the clouds essentially absorb some of the infrared radiation emitted by the Earth and re-radiate some of this back down to the planet. This can lead to a warming effect in the local area. So essentially what I'm saying here is clouds and changes in clouds can have complex effects on the climate system, and changes in cloud coverage can lead to warming or cooling in the polar region. Now the next one is kind of linked to clouds, and this is looking at aerosols and pollution. So aerosols are particles of liquid or solid suspended in the atmosphere. And aerosols in the lower atmosphere do not tend to last too long because over time they get deposited. They can either get rained out or they can just fall out through gravitational deposition, or just eventually, due to random motion, they hit the ground and come out of the atmosphere. And aerosols are important in this topic because they are able to interact with light, directly and indirectly, depending on the aerosol. So, the burning of fossil fuels tends to release sulfur dioxide and sulfate aerosols. So the reduction in pollution in Europe over recent decades, due to implementation of clean air policies, these policies were implemented mainly to combat acid rain, because the burning of coal emitted a lot of sulfur dioxide into the atmosphere. This would mix with rain and form sulfuric acid, and this would fall out of the atmosphere as rain and cause harm to buildings and structures and soils and lakes. So these sulfate aerosols are able to interact with light directly or indirectly. So directly, sulfate aerosols are able to interact with incoming solar radiation from the sun. So shortwave radiation, light radiation, whatever, coming from the sun. They're able to scatter some of this back. They act as a slight mirror, able to scatter some of this back out into space, and this can lead to cooling. Additionally, water vapor likes to condense out onto a nucleus. So when you think of water vapor in the atmosphere, when it cools down, it doesn't tend to clump together to form a liquid from a gas by itself. It tends to form onto an already existing nucleus, such as a sulfate aerosol. So sulfate aerosols can actually seed clouds, and water vapor in the atmosphere much more readily condenses onto these sulfate aerosols than they do just homogeneously. So with a presence of sulfate aerosols, you can form more and more clouds. That's why in polluted regions you tend to see formation of clouds. Now, as from the last feedback, increasing cloud coverage can reflect solar radiation. So it's thought that the reduction in pollution around Europe has been shown to kind of unmask some of the warming in the polar region. So we're getting less of this reflectance out of space, either directly through the sulfate aerosol or indirectly through the formation of clouds. So with less pollution, we're kind of seeing unmasking this warming, because it's known that aerosols and the clouds that they produce can have significant reductions in the temperature. Now, the next feedback I want to talk about is the temperature feedback. Now, this one is fairly intuitive if you have done any physics, but maybe not so if you haven't. But the Earth, as you know, emits radiation, and this is known as the terrestrial radiation. Because the Earth is around 300 Kelvin in temperature, it emits in the infrared spectrum. Now, the Sun is significantly warmer at around 6,000 Kelvin, and it emits primarily in the light going into UV spectrum. So, essentially, the Earth emits radiation at its temperature, and a warmer body will emit more radiation than a cooler one, and it emits at shorter, higher energy wavelengths. And this can act by bringing the temperature of the hotter thing down. So if you increase the surface temperature, then the surface will emit more radiation, and this can bring down the temperature again. However, this happens differentially at different temperatures. So in a more polar-like region, such as around a temperature of minus 30 degrees centigrade, an increase if only of 1 watt per meter squared radiative forcing can be offset by an increase of 0.31 degrees Celsius. However, at 30 degrees, and more in the tropics, an increase of the same amount of radiative forcing, 1 watt per meter squared, can be offset by only half this at around 0.16 degrees Celsius. So at higher temperatures, you need less warming to emit the same amount of energy back out to space. So when I say radiative forcing, 1 watt per meter squared is basically the amount of energy per unit surface area of the planet that is increased due to forcing from carbon dioxide, for instance. So if you've got more carbon dioxide, you're increasing the energy per unit surface area by, for instance, 1 watt per meter squared. So an increase of a given quantity of energy per unit surface at the poles, you need a higher increase in temperature to offset this warming than you do at the tropics. And this can lead to an increased amount of warming at the poles compared to the tropics. Now, the next feedback mechanism is the water vapor feedback. Now, this is due to larger changes in the water vapor content of the Arctic atmosphere than of the tropics atmosphere. Increases in water vapor in the Arctic region are expected with increased air temperature and reduced sea ice coverage. Water vapor is a very powerful greenhouse gas. It effectively absorbs long-wave radiation, so the radiation emitted by the Earth, the terrestrial spectrum, infrared radiation, and emits a portion of this back to the surface, which can lead to further warming, so just acts as a greenhouse gas. So the larger increase in water vapor in the atmosphere of the Arctic compared to the tropics, it causes a greater increase in radiative forcing due to water vapor in the Arctic region compared to the tropics region. So this can increase the temperature greater in the Arctic than further down. Now, water vapor is a very interesting greenhouse gas. In fact, it's responsible for the majority of the greenhouse effect on Earth. However, its concentration is not usually directly affected by human activity. And we don't really consider it as a greenhouse gas we worry about too much because its lifespan in the atmosphere is only a few days, and we do not see very big changes in the amount of water vapor in the atmosphere over time. Which with other greenhouse gases, we are seeing significant increases in the concentration in the atmosphere over time. So the final feedback is the lapse rate feedback. Now, the lapse rate is basically as you go up in altitude, the temperature of the atmosphere changes. So it's the rate of change per unit altitude, so per kilometre, for instance. And the lapse rate is not the same everywhere. And for the greenhouse effect to work, the temperature of the atmosphere in the region that radiates to space, so where the greenhouse gases are, has to be less than the surface. So in the tropics, convection causes mixing of air and reduces the difference in temperature between the surface and the troposphere. So the troposphere is the lowest level of the atmosphere. In a warming climate, rising air releases more energy, and this is because you have the process of condensation of water vapor releases energy. It's called latent heat. And this can warm the troposphere, but it doesn't warm the surface. So essentially, you're reducing the difference in temperature between the surface of the Earth and the troposphere. And this reduces the greenhouse effect. It's a negative feedback, as the outgoing long-wave radiation at the top of the atmosphere is increased, so more energy is lost to space. However, in the polar region, you've got less convection, because the Arctic, there's much less convection. So there's less coupling between the lower atmosphere around the surface of the Earth and the upper troposphere. So therefore, when you increase the temperature of the surface, you're not so much increasing the temperature of the troposphere higher up. So you've got less warming there, but you've got more warming at the surface. And this tends to increase the greenhouse effect by basically the amount of outgoing long-wave radiation doesn't increase as much. So you've got positive feedback. And this can warm the climate in the polar region. And it's thought that the lapse feedback effect and the ice albedo effect are the two most powerful feedback effects that are causing Arctic amplification. So, with that is everything for this episode of the Curiosity Monkey podcast. I do hope you enjoyed this episode. It was a bit physicsy, and I appreciate that, but I think it's a very interesting topic, and also maybe not so well known about. I think people tend to know that the Arctic is warming faster than the rest of the world, but not necessarily why. And I listed and went through some of the mechanisms of to why. And yeah, I think it was actually very interesting how there's so many different things that can play into this. And the climate system as a whole is very complicated, and every bit is tied with something else. So a change to one thing can cause changes to other things. And this is partially why trying to model the climate is very challenging, especially in the long term. If you don't have every interaction between the physical processes nailed, then often your climate models just will not predict very well. So yeah, that's everything for this episode of the Curiosity Monkey podcast. I do hope you enjoyed this episode. If you do wish to contact us for feedback or episode suggestions, you can email us at thecuriositymonkey1@gmail.com or on Instagram at thecuriositymonkey. So give us a follow, give us a rate on Spotify, and thank you for listening. Goodbye.